Hello, everyone. Good afternoon. We are here to discuss how we are authenticating and authorizing every connection at Uber. A quick intro about us. My name is Matt, and I have Yangmin here with me. We are from Uber. We represent engineering security within Uber. We'll talk about how we spent the last 2-3 years building a service mesh, which led us to actually authenticate and authorize every connection. A quick overview of the agenda. We'll start with the goal, why we are doing this. We'll talk about the solution that we implemented, some of the things that we did to improve the adoption of the solution. We'll talk about some of the key lessons that we learned, and then finally end with some of our takeaways. Before we jump into why we're doing this, I do want to set some context on Uber's landscape. We have a pretty large tech stack that we operate at Uber. Back in 2015, Uber adopted a microservice-based architecture. So in the last 10 years or so, we have built over 7,000 microservices. We are operating around 7,000 databases, and also almost 500,000 data jobs. In addition to that, we leverage multiple RPC frameworks. We utilize around 5 languages or so. And last but not the least, we're not 100% on Kubernetes yet. We have several container orchestration systems. Some of them are open source, some of them are also built in-house. So what you can see here is we operate a large-scale, highly heterogeneous LAN system. And one of the key things to notice over here is that we are also leveraging several open source technologies. Keep this in mind because this is going to influence the solution. So among this large tech stack, we have several security and compliance requirements that we need to meet. And in order to do that, we have to authenticate and authorize every single service call within Uber. So this is our goal, right? Back around 2020 or so, or 2019, 2020, roughly 5 or 6 years ago, we actually started building a solution which is completely library-based. And what this library does is we ask all the service owners at Uber to go ahead and adopt this library. So if a service A is calling service B, then on the caller side, this library goes ahead and works with SPIRE, gets a X19 certificate from SPIRE, follows SPIFFE standard, utilizes that to create something called a JOT token. Nothing fancy there. And this JOT token is utilized to perform the authentication. On the caller side, on the callee side, on service B, the token is verified, so authentication is complete. And then the caller is extracted from the token, and we do authorization over there. To perform authorization, we have authorization policies put in a policy management system, which we have built in-house, homegrown. Similar to cloud IAM solutions, we have an authorization system for managing policies. So this is a solution that we built back in 2020. And you might think that this will work. But in fact, we ran into several problems there. These are the 3 key problems that we ran into. First is once we put this library in place and we asked people to adopt, adoption actually stalled. And it stalled at around 10%, right? And there's a key reason why it stalled. The main reason here was we were asking engineers, we are around 6,600 engineers at Uber now. We were asking all these engineers to go ahead and amend their systems by adopting this library. And that was a big operational load that they need to take on. So that's one of the reasons why the adoption stalled. The second thing is around the operation load and the maintenance burden. Since the library is within these services, whenever we have to do a fix, like a security fix or even a bug fix, now we have to go chase these 6,000 engineers again to go ahead and update the library within their system. So it became a burden for us to make any patches or so on. Beyond that, the other part was around, we built this library for Golang and Java, but we have Python, JavaScript, and one more other language where we didn't have this library. So it became difficult for us to actually have a consistent fix or consistent solution for these different languages. We also had some bugs in one language but not in the other. So it was also inconsistent. Some metrics went missing and a few other issues as well. The third one is around the technical constraint with open source systems. When I spoke about the landscape before, we have multiple open source systems that we leverage for scaling the Uber tech stack. Some of these open source systems are pluggable and some of them are not. So it became incredibly hard to actually adopt a library-based solution in some of the open source systems, and that was a technical blocker. So we had to rethink our strategy, and we came up with the service mesh-based solution. The solution is based on Envoy, and it is heavily inspired by Istio's architecture. The diagram looks very similar to the one that I showed before, but there's a key difference here. The key difference is that there's no library within the service. Instead, that logic of authentication and authorization is moved to an on-host proxy. So Envoy does all of this transparently behind the scenes. In addition to authentication and authorization, we're also doing encryption in transit because all of these connections are mTLS based. Let's revisit the problems again. Low adoption, operational burden, and the technical constraints. Since this is an on-host proxy, there's no burden on the service owners to go ahead and adopt libraries. So the low adoption problem got solved over there because we don't ask engineers to adopt libraries anymore. The second part on the operation burden, Envoy is managed and maintained by one team. So it is easy for us to have any fixes, security upgrades, and so. The third one, around technical constraints, since we operate at the network layer, there's no need to go ahead and change any of the open source systems. So in effect, we actually solve these three problems centrally without asking any of the rest of the company to do any work. I'll hand over to Yangmin to go a little bit deeper into the architecture.
Thanks, Matt. So let's deep dive into the actual technical architecture a little bit here. As you can see, we will be focusing on the data plane here. That's the most interesting part, and that is also a part we use a lot of the open source software like Envoy, SPIRE, and other stuff. On the left side of the diagram, it shows we have the Envoy and Envoy Manager deployed as a host agent. Envoy Manager is our home-built program written in Go that is responsible for managing the lifecycle of Envoy and its configuration, and also talks to some other host agents to fetch certificates and other stuff and push those things to Envoy. We also built a layer between the service and the Envoy to transparently redirect the traffic from the service to Envoy. As we mentioned before, we do not want the service owner to make any code and configure changes. So how do we get that traffic from the service to the Envoy? We rely on this traffic redirection layer. The other two major parts is on the client side, host 1, we have this outbound functionality built into Envoy that would inject the identity when it receives the connection from the service and use that to establish mutual TLS connection to the destination Envoy on the remote host. On the right side of the diagram, when the mutual TLS connection hits the Envoy again, we build a functionality into Envoy to enforce authorization policies on the inbound. We only forward the traffic to the destination service if it is fully authenticated and authorized. We will be focusing on the outbound and inbound functionality in this talk because that is most relevant to security. But if you are interested in the traffic redirection, you can look at the Envoy account given by our awesome networking team, and it talks great details of that part. Okay, so zoom into the outbound. How do we inject the identity? So the major problem here is when the TCP connection is redirected from the service to the Envoy, how does Envoy know who is the caller? If you know about the TCP connection, you know it gives you limited information, right? Source IP, source port, destination IP. So how do you know it's service A or service B initiating that TCP connection? To solve this problem, we first rely on the fact that we allocate a unique integer as the network class ID of each of the container when it is started on the host. And we also implement a custom eBPF program that would copy this network class ID integer to the SO mark option of the outbound TCP connection originated from the service. Next, we modified Envoy to implement filters and other things to read the network class ID integer from the SO mark of the TCP connection. With that integer, we can look up in a table that maps the integer to the service identity. In this case, Envoy knows that this connection is originated from service A, and that connection is from service B. Last, we have the Envoy manager talking to the SPIRE agent via the dedicated identity API to fetch the certificates. We have to use this API because it is fetching certificates on behalf of the workloads. That's why it is called dedicated identity API. And then we push the certificates to Envoy, and Envoy uses it to initiate mutual DLS connection to the destination, wrapped in proxy protocol to pass the original destination port used by the service. Next, let's zoom in the inbound side of this diagram. When the mutual DLS connection hits the Envoy on the remote host, the most important problem we need to solve here is how do you know which policy to enforce and how do you enforce it actually? To solve this, we also rely on some of the unique facts at Uber that when we start the service on the host, we always pre-allocate the ports used by that service container. And that information is passed as part of the container spec so that Envoy manager can read it in addition to the auth policies and push those things to Envoy. By the way, we use the Envoy RBAC filter to enforce the authorization policy. At runtime, when the TCP connection hits the Envoy proxy, we have the custom changes to extract the original destination port from the proxy protocol. That port tells us which destination service is actually being accessed by the original service. And it also allows us to look up in a table to see, for example, port 8000 is used by service A, and we would enforce the policies of service A. Last, it would trigger the RBAC filter we push it to Envoy to actually enforce the policy of the service. We only forward the traffic to the destination service when the caller is fully authenticated and authorized. With all those technical solutions in place, the next major question is how can we actually get everyone to adopt it? That, to be honest, is probably the even harder problem than figuring out a solution. So we have three main paths here. We want to build end-to-end observability so that we know who is calling what. We want to have a good dev experience so that our users, they are happy to adopt. And we want to have a safe, gradual rollout to ensure reliability. We do all of this, and it's important because eventually there will be a human touch point to manage the policies as a service owner. The very first part of this adoption journey is to have a good observability. This is essential and critical to support our adoption and also to support troubleshooting so you know who is calling what and when, and to build the monitoring, dashboard, alerting so that you know when the authorization is succeed or failure. In the native Envoy RBAC filter, unfortunately, it doesn't emit the tags to tell you who is calling what. It emits the metric to tell you if the connection is allowed or denied. So we enhanced the RBAC filter to also emit the tags with the dynamic caller and the callee together with some other useful information that will be used to support our monitoring, policy authoring, and alerting and other stuff. As you can see in the diagram comparison, On the right side, we have all the tags emitted of the, like the service A is calling service C.
Yeah. The next part is around how to get the developer experience sorted out. So if you have thousands of services, and then you go to the developer and say, hey, go author authorization policies for these thousands of services, it's going to be painful. And not just painful, it's unreasonable to ask everyone to go ahead and add authorization policies for 7,000 services. So we had to get really creative over here. In order to do this, what we did is the observability that Yangmin just mentioned. We used those metrics, and we built a policy generation system. So basically, what we're doing over here is that we are observing all the traffic. Our Envoy has this feature called RBAC in shadow mode, so we're utilizing that. So everything is in shadow mode, no enforcement yet. We are using all of that observability metrics to go ahead and figure out all the edges and create authorization policies for all the services. With this, we are able to create authorization policies and then hand off to the user as a last step. Hey, go ahead and take a look, review it, click a button to enforce it, and at that point, the authorization policy is enforced for the service. We did this as a pilot adoption step within our own team, friends and family teams. And what ended up happening is, even though we had all of this built out, a lot of the teams did not want to review. That itself was considered as a burden. So we changed our strategy a little bit over there. We said, we force teams to review when their asset or their service is critical. For the non-critical assets, we actually didn't ask anyone to review. Instead, we automatically landed the policies because we are very confident that the policies that we authored are correct. The second part around the developer experience was around reliability. Generally, developers care about reliability of their system, so adding a policy, if the policy was incorrect, it would have broken the system. So we want to be cautious over here. In order to ensure that bad policy changes do not disrupt the system, we came up with a comprehensive solution, which covers 3 different areas: pre-rollout, during rollout, and post-rollout. During the pre-rollout stage, what we do is whenever there's a policy change, we actually do something that we call policy simulation. What it does behind the scenes is it's computing an impact analysis. If this policy change were to be rolled out, what would happen in that cluster? So we have a blog about this, which we published recently, a couple of months ago. There's a link down there at the bottom. I won't go into details, but this is pretty much a big lifesaver on looking at what is the impact of policy change, warning the user if there's any negative impact so they can basically abort the deployment. The second part is during the rollout itself. During the rollout, we have multiple different zones within Uber that we operate. What we did is we have integrated the system into Uber's internal change management system, where after every zone is rolled out, we actually have a soak time. And after the soak time, it continues to the next zone. The good part is with all the metrics and alerts that we have configured, if there's an increase in the denial rate, then we will be able to go ahead and roll back the policy so that we are not breaking the system. Assuming the rollout went well, right? The next part is around what happens post-rollout. So we build a set of tools for developers to interact with our system. This include a UI, CLI, and so on. In addition to that, we gave them a big red button, which is, in case something happens after all of this, there's a way you can come to the system and say, disable the authorization policy in case the system has degraded. And they are able to disable within a few minutes. The next part is around gradually rolling this out across the entire company. So like I said, we have thousands of systems that we need to roll this out to. What we did is we looked at business criticality, the organization or the team that owns the system, and also the asset type or the service type. We roll out to stateless first before we roll out to the databases. Using this, we rolled it out over the course of, I think, almost a year. We started the rollout late last year. As of today, this is metrics from yesterday that we grabbed. We are authorizing over 2 million connections per second within our system. And these are all service-to-service calls. We'll move on to some of the lessons that we learned. We have 5 lessons that we are going to talk through. There are so many lessons that we learned across the last 2-3 years, but these are the top 5 that we're going to go through. The first lesson that we learned is during load testing, and that is around this race to distribute identity. So when a service is being launched through Kubernetes, what happens is Kubernetes works towards launching the service container on the data plane. In parallel, we use SPIRE for distributing certificates. SPIRE is trying to issue the certificate and distribute it to the data plane. What we observed is that Kubernetes always wins. Kubernetes always launches a container way faster than SPIRE distributing the certificate. And this is not great because the service starts making outbound calls and the certificate is not there. So in order to fix this, we actually changed the architecture, where we said, we are going to issue the certificate and use Kubernetes secrets to distribute the certificate to the data plane. And this is a major change because the latency of distribution that we were observing was in the order of almost a minute, 70 seconds or so. With this change, we were all able to bring it down to almost 1 or 2 second range. And this, basically, we were able to fix this problem. I'll hand off to Yangmin for the remaining lessons.
Thanks, Matt. So the next lesson, is about how do we handle some of the client retry storm. So the problem is upon the authorization denial, because it happens at the TCP level. Some of the clients, they do not understand this is being closed because of authorization denial. So they have some kind of buggy logic to retry in the busy loop. This is not only increasing the connection rate to a very high level, but also causing a lot of CPU usage in the proxy. As you can see in the diagram, we have this buggy client retrying very aggressively when their connection is being authorized denied. The connection rate jumps to 400, and the proxy CPU usage jumps to like 45%. We introduced a solution by delay like 1 second before we actually close the TCP connection upon authorization denial. This helps to drop the connection rates literally to 1 connection per second for those callers that will be denied by authorization. And consequently, it drops the proxy CPU usage to just like 1%. This is important to help us to protect our proxy from being overloaded by those like misbehaving clients, because the proxy is shared by a lot of different services on the host. Next lesson we have is we really need to isolate the policy change impact across services, because again, the Envoy proxy is shared by services running on the host. Our goal is when you change a policy for service, the impact should be limited to that service itself and not any other services on the host. We implemented this in a way so that when we are pushing changes in the Envoy, only the services with that policy change will be affected and not any other services. But soon we observe some issues with this implementation. For example, even for the service having the policy changes, the connections may actually not be relevant to the policy change. For example, you are adding a caller to your authorization policy. You are not removing anything, so why would you cause any disruptions to the existing connections, right? Existing callers, they are already allowed, and they are continuing to be allowed by the new policy. This is a problem because for some latency-sensitive applications and services, it's not acceptable to close those existing connections at all. For example, we cause a small outage for our Redis and Kafka. It causes a latency spike when people are pushing policy change because it closes existing connections to those services. So we made improvements to just not drain or close the existing connections when we are pushing policy changes. And we also add jitter to smooth out when we are applying the policy change. It will spread across all the instances of the services smoothly instead of applying them all at once. But this gives us a new problem, like when you are removing a caller from the policy. If we are not closing existing connections, it is a security concern that the removed caller is not delayed in time, because an existing caller may no longer be allowed by the new policy. So we made further improvements to fix this in Envoy and our manager, so that when you are removing a caller from the policy, we will inspect and proactively block that caller if that caller is no longer allowed by the newer version of the authorization policy, without impacting any other existing callers. The next lesson is an interesting one. So after we put everything in running, we realized some callers they are missing in our generated policy. We dig into this and we find out because the policy generation is heavily relying on the metric output by the proxy. But sometimes we find out the metric are corrupted because it doesn't have the service tag. We troubleshoot this and find out those corrupted metrics, they somehow have all their tag collided into the metric name. They are no longer as exported as tag. So we have to dig into Envoy code and we find out this is simply because Envoy doesn't support the dynamic tag during the hot restart. Hot restart means we start a new Envoy that will head off the old metrics from the old Envoy to the new Envoy. It is deep in the code, not mentioned anywhere in documentation, that this particular feature is not supported. The fix is actually simple. We just modify Envoy to drop those metrics with the dynamic tags, and we let the new Envoy to recreate it when it is actually needed. In that case, it will always ensure it has a correct tags. The last lesson we want to mention is to ensure reliability, we created alerts to notify service owner when the authorization delay is happening. It turned out to be quite noisy in some times because people get paged at midnight and they do not have clear action items. And this also is causing some trust issues from user because they don't take the alerts seriously after they get paged multiple times. So we analyzed the problem, we fine-tune the threshold, we reduced the number of the alerts. We do not page the calling service because it's not really actionable by them. We still page the caller because that's their responsibility to fix the policy. And we also provide a tool and API to help the user to resolve those alerts automatically. So with all those things, we have some high-level key takeaways, I think. First of all, for a project like this, leadership support is critical for the success. You need leadership support not only from your org, but also from other orgs or potentially even the entire company. You need to partner and collaborate closely with your product teams because they are the user to adopt your products. Take their feedback seriously and make meaningful improvements to solve their concerns. Last, we also collaborate with our key stakeholders at Uber to make this solution possible, especially the networking team, observability team, because it's such a big project that requires all different layers to work together. Next, every security interaction with a human is challenging. So if you are pushing out something like this, try to optimize it to reduce the decentralized efforts and make it as centralized as possible. And if you cannot do that, make your user dev experience as frictionless as possible. Last but not least, when you are retrofitting this security solution to the existing system that has thousands of services already running, it will be hard. You will have legacy code, technical debt, and even engineering mindset that make it very challenging to adopt new security solutions. So if you have a chance to do it sooner, do it now before it's too late. Last, we are also looking into some new improvements of our systems. Particularly, we want to involve the technical capability. Our networking team is looking into making the Envoy proxy of host, and also looking into the CNI to provide container network namespace. And our security group is evolving the authorization to provide L7 capability. We are also expanding the use case to cover not only service-to-service communication, but also personnel-to-service communication, so that we have the single solution for both major use cases. Last, we are still looking into solutions to simplify our policy management. As you can see, currently most of these policies, they are static, they are authored and managed manually by the end users. We want to leverage AI and some other tools to provide more adaptive authorization so we can reduce the management burden and friction from our service owners. That's all.
That's my
questions.
Yeah, go ahead.
So you mentioned you're running over 7,000 microservices, but I saw so I'm curious in regarding to the metrics, right? So how does the cardinality look like when you have Envoy per host, right? So you can have millions of different hosts and destination pairs. So what's your cardinality look like?
You're asking about the cardinality about the metrics?
Yeah, one of the challenges when you move Envoy to be per host is now that, as opposed to sidecars, right, you have many different destinations the same Envoy can handle. So I'm just wondering if you hit any cardinality issues or if you have looked into this.
Let's just say that we have a highly scalable metric system called M3, and we rely on that. In terms of cardinality, yes, we are looking at every service edge, and we are basically having metrics around it. I think it's in the millions range, if I recall correctly.
So there's no issues with the system you're using?
Yeah, we can add something.
That's a really good question, because we do hit some of the quota issues at some point. We have actually some lessons, but not listed here. The first one is we include the service in the metric, and we don't include the host in the metric. You either have the service or the host, but don't put both of them in the metric. The second thing is we looked deep into the metrics emitted by Envoy, and we exclude those that we do not need. You will be surprised how many metrics are exported by Envoy by default. So if you exclude a lot of those things you don't need, you actually get a lot of quota back. The third thing is we integrate with some internal systems that we aggregate those metrics to drop some tags to emit new metric. For example, we have an aggregated metric to tell if we have a connection denial happening in this strong. That metric doesn't need the service tag because we can build another alert on this. So with those things, we are able to make this a manageable, yeah.
Okay. Thanks.
Thanks for the presentation. Could you briefly speak to the traffic redirection layer? Did you leverage the CNI to do that, or is it some other thing?
Sorry, about the traffic direction, you mean?
Right. You said that you had a traffic redirection layer to transparently route traffic through Envoy from services without the service owners having to change anything in their code.
So you mean how we did that, right?
Right.
Okay, so I will be talking on behalf of our networking team. So basically, we have some routing rules to redirect the service traffic to some, I think, loop-back interface. We have custom eBPF to use, I think there's a feature in eBPF to assign the socket to forward the traffic directly between two sockets. And we have also built some manager to sync those information, like the socket used by Envoy and the socket used by the service, so that the eBPF program knows which socket's traffic should go to the Envoy to handle it. That's that's a very high level.
So it's eBPF program at the host level doing
Yes, eBPF and some custom routing rules.
Thank you.
Yeah.
Hi, I was wondering why you chose to run Envoy as like a shared Envoy on host versus like a sidecar container.
I can. Okay. So I used to work in Istio. So I think the first thing is it costs a lot to run Envoy as sidecar because the resource it consumes memory, CPU. We have so many services. We have millions of containers. If you have to run it every container, that cost will be huge. Secondly, it's also about how the networking look like at Uber. We currently do not use pod network namespace, so every container shares the host network. It would be very challenging to even implement sidecar in this network model. And third, we already have some homegrown proxy that runs as a host agent, but it only forwards traffic on the client side. So we want to be more compatible with that as well.